Hi, I'm Roland Minton. These are some of my favorite math stories. In this episode, mathematics is game shows. We'll take ideas from the excellent book, The Monty Hall Problem by Jason Rosenhaus. I highly recommend it. The problem references Monty Hall, the longtime host of the game show Let's Make a Deal. One day I joined a lively discussion in the hallway in Trexler. Some of my colleagues had seen a probability problem stated, poorly as we shall see, in a Sunday newspaper supplement. The problem is now famous enough that you have probably encountered it. As stated in the paper, suppose you're on a game show and you're given the choice of 3 doors. Behind one door is a car, behind the other's goats. You pick a door, say number 1, and the host, who knows what's behind the doors, opens another door, say number 3, which has a goat. He then says to you, do you want to pick door number 2? Is it to your advantage to switch your choice? My initial reaction was to say no, there is no advantage to switching. There are now 2 doors left, and you don't know which doors the car's behind. It's a 50-50 choice, I thought. The author of the newspaper article, however, said to switch, that there was a 2/3 probability of the car being behind door number 2. This was followed by an explanation that didn't convince me at all. Most of the mathematics community reacted the same way, and the author was flooded with letters from outraged readers, many flouting their mathematics degree. Now, as you may know, in the most basic interpretation of the problem, the author was correct, and you should switch. Here's my favorite explanation for why. The car is equally likely, 1/3 probability, to be behind each door. Let's look at each of the 3 possibilities. If the car is behind door 1, the host opens up one of the other doors, but you should not switch. If the car is behind door 2, the host opens up door 3, and you should switch. If the car is behind door number 3, the host opens up door 2, and you should switch. Switching wins 2 out of 3 times, since the host shows you which door to switch to. Did you see anything wrong about that logic? I didn't until reading Rosenhaus's book. There's a subtle ambiguity that needs clearing up, and it has to do with what the host does if the car is behind the door that you chose, door number 1. Now, how could this matter? Well, suppose that the host always opens up door number 2 if the car is behind door 1. You choose door 1, and the host opens door number 3 to show you a goat. You now know that the car is not behind door number 1. If it was, door 2 would have been opened. You should 100% switch to door number 2. This is more complicated than it looks. Most people assume that if the car is behind door number 1, then the host randomly, 50-50, has one of the other doors opened. If the host does not follow a 50-50 rule, there may be information gained that changes the odds. One way to analyze this is using some rules from probability theory. In particular, we need conditional probabilities. As a simple example, what is the probability of rolling a 4 on a standard 6-sided die? There are 6 possibilities, and we want one of those 6, so the probability is 1/6. What is the probability that you rolled a 4 if you are told that you rolled an even number? Now, this new information, given an even number, reduces the possibilities to 3, a 2, a 4, or a 6. So the conditional probability is 1/3. We will use a bar for the given part, so what we computed is written as P of 4 given an even number. The general conditional probability rule is the probability of A given B is the probability of A and B divided by the probability of B. In our example, the probability of 4 given an even number is the probability of 4 and an even number divided by the probability of an even number. Now, 4 and an even number is the same as 4. 4, after all, is an even number, so that's 1/6. Probability of an even number is 1/2, and 1/6 divided by 1/2 is 1/3. The answer we already got. Now it's going to get a little bit messy. We will use C1 for the car being behind door 1 and H3 for the host opening door 3. We want to compute the probability of C1 given H3, the probability that the car is behind door 1 given that the host opens up door 3. In other words, we should not switch. This will be the probability of C1 and H3 divided by probability of H3 using our conditional probability rule. We'll now get a little bit tricky and rewrite the probability of C1 and H3 as the probability of H3 given C1 times the probability of C1. We'll divide by the probability of H3, which we rewrite as our previous expression, plus the probability of H3 given C2 times the probability of C2. We don't need C3 because probability of H3 given C3, well, the host is not going to open up door 3 if the car is behind door 3, so that's a 0. We can fill in some stuff. The probability of C1, probability of C2 are both 1/3. Probability of H3 given C2, that's the probability that the host opens up door 3 with the car behind door 2. That always happens. That's probability 1. So the 1/3 will cancel out, and that leaves the probability of H3 given C1. Actually, I'm getting tired of saying that. Let's just call it P. So I've got P, drop the 1/3 on top. P, again, drop the 1/3 plus 1 on the bottom. So the probability of C1 given H3 is P over P plus 1, where P is the probability that the host opens up door 3, given that the car is behind door 1. So it does make a difference what the host does in that ambiguous situation. Now, some examples. If the host opens up a random door, P is a half. Our fraction is a half divided by a half plus 1, which is 1/3. That is, we have the right door with probability 1/3, but we get the car by switching 2/3 of the time. And that's the classic answer. Now, if the host always opens up door 2, P is 0, and our probability is 0 over 0 plus 1, that's 0, we should always switch, which we already found out. Now, if the host always opens up door 3, P is 1, our probability is now 1 over 1 plus 1, which is a half. And that's the 50-50 case that most people expect when they first see the puzzle. So the probability of winning by switching can actually be anything from 1/2, it doesn't matter, to 1, you should definitely switch. This puzzle is way more interesting than any of us in the hallway knew when it first came out.